Welcome, everyone. Today, we're going to pull back the curtain on a fundamental mathematical concept that, believe it or not, powers our entire modern economy. We're going to move way beyond abstract theory to see how a single tool from calculus is absolutely essential for making decisions in a multi-trillion-dollar industry. So, let's start with something we've all done. You've ordered something online and you're glued to that little tracking icon moving across the map. The secret behind that amazing precision, its ability to tell you what's happening right now, this very second, it's not just GPS. GPS is great for telling you the where, but the how fast, at this very instant, well, that comes directly from a core principle of calculus.
And that tool that makes it all possible is called the derivative. Now, before anyone gets intimidated by the term, let's just break down what it actually does in a business setting. Think of the derivative as a precision instrument. Its entire job is to measure an instantaneous rate of change. And in business, I don't care if you're in logistics, finance, or marketing, understanding the rate of change is, well, it's everything. Okay, let's really dive into this. To properly build our business model, we first need to get crystal clear on two key ideas that logistics managers live and breathe every single day. We're talking about position and velocity. Now, truly grasping the distinction between these two is the absolute first step toward any kind of optimization.
Okay, first up, we have what's called the position function. The best way to think of this is as the master map of a delivery truck's entire route. Mathematically, it's a function, we'll call it P of t, where you can input a specific time, that's our t, and the output, P of t, gives you the truck's exact location, or its distance from, say, the warehouse. This is the foundational data. It answers the static question, where is my asset right now?
Second, we have velocity. Now, as future business leaders and analysts, it is absolutely critical that you understand that velocity is not the same thing as speed. Speed is just a number on a dashboard, 60 kilometers per hour. That's it. Velocity includes direction. For our logistics model, it tells us how fast the truck's position is changing at one specific instant and in which direction it's heading. It answers the all-important dynamic question, how is its position changing right now?
And here it is. This is the crucial link. As this principle from our source material states, to get from the static where of the position function to the dynamic how fast of velocity, you calculate the derivative. The derivative is the mathematical engine that transforms a function describing a location into a brand new function that describes its instantaneous rate of change. It's how we get from a snapshot to a live video.
All right, so let's put this into practice. I want you to imagine you're the logistics manager for a huge delivery company. Your key performance indicators, your KPIs, they're all about efficiency. We're talking on-time delivery, fuel costs, asset utilization. You absolutely need to know not just where your trucks are, but exactly how efficiently they are moving. So here is a hypothetical position function your analytics team has developed for a truck on a specific route. This equation here, it describes the truck's distance in kilometers from the main warehouse at any given hour, t. Now, looking at this, you can easily calculate its location at any time. You can plug in t equals 1, t equals 2, but what you cannot see is its exact speed at any specific moment. That information is hidden. Now, here's the business problem you have to solve. A priority client calls, and their entire assembly line is on hold, waiting for this shipment. The average speed for the last 3 hours just isn't good enough. That's old data, it's skewed by traffic, by the driver's lunch break, it's useless. They need a predictive ETA. And to get that, you need the instantaneous velocity. So how do you find it? We follow this exact procedure. Step 1 is our given, the position function. Now, step 2, this is where the magic of calculus happens. To get the velocity function v of t, we apply a fundamental rule of differentiation called the power rule. The rule states that for any term ax to the power of n, its derivative is n times a times x to the power of n minus 1. Let's apply that to our first term, 2t squared. Here our n is 2 and our a is 2, so we multiply 2 by 2 to get 4, and we reduce the exponent from 2 down to 1. That gives us 4t. Easy enough. Now for the second term, 5t. A very common mistake here is to forget that this is really 5t to the power of 1. So in this case, n is 1 and a is 5. We multiply 1 by 5, which is 5, and we reduce the exponent from 1 to 0. And as we know, anything to the power of 0 is just 1, so we are left with just 5. That gives us the powerful new velocity function you see in step 2, v of t equals 4t plus 5. The calculus part is done. The rest is just simple algebra. In step 3, we substitute our specific time t equals 3 into this new function. 4 times 3 is 12, plus 5 gives us 17. And step 4 gives us our action or business intelligence. At exactly the 3-hour mark, the truck is moving at 17 kilometers per hour.
That right there illustrates the incredible power of differentiation.
So we've just figured out the truck's velocity is 17 kilometers per hour. As business students, your very next question must always be, so what? Who cares? Why is knowing this precise number so much more valuable than just knowing the truck's average speed over the last few hours? Let's break down the strategic business impact of this one single calculation. The difference is, frankly, a total game changer. As you can see here, we've moved from an era of just making general estimates to an era of surgical precision. In the past, managers worked with averages, which are reactive. They only tell you what already happened, and they're easily skewed by things like traffic. But now, with instantaneous velocity derived from calculus, managers can be proactive. They can make real-time surgical decisions. They can reroute a truck to avoid a sudden accident, give a customer an ETA that's actually accurate to the minute, and even optimize fuel consumption based on moment-to-moment performance. It saves time, it saves fuel, and it saves money. So here's the crucial point. Understanding this one concept from calculus directly allows a business to be more competitive. As this slide highlights, it translates directly into a stronger, more reliable, and ultimately more profitable operation. This is data-driven decision-making in its absolute purest form. And it's exactly why understanding these mathematical tools is no longer optional in the modern business world. It's a requirement. And the scale we're talking about here is just immense. This is an industry worth well over $10 trillion. An industry where tiny, single-digit percentage gains in efficiency, gains driven directly by this kind of mathematics, translate into billions, with a B, of dollars in savings and new value. The little calculation we just did isn't just a textbook exercise. It's the fundamental building block of a massive global economic engine. So this leaves us with a final thought to chew on. We've seen today how calculus isn't just some abstract subject you have to survive in college. It's a practical, powerful tool hiding in plain sight. And this concept of the derivative, of measuring instantaneous change, it's universal. In finance, it's used to value complex stock options. In economics, it defines marginal cost and marginal revenue, which are the absolute cornerstones of any pricing strategy. So the next time you track a package, I want you to remember the derivative that's making it all happen, and start to ask yourself, where else is this powerful idea shaping my world?